Hey guys, this is Professor Janacek. Looking at integration techniques, we have a couple of types of substitution. One is regular substitution, often referred to as U substitution, and the other is inverse substitution. Let's take a look at the difference between these two techniques. For regular substitution, if we're integrating f of x dx, the first thing we'll do is we will let u equal some function of x. And then du is some derivative. Of course, with dx, chain rule and all. Once we've come up with u and du, then we will rewrite our integral in terms of u. It turns out that this can be a little bit difficult. And this is often where we make mistakes, students make mistakes with integrals, with this technique. Now, once we've got that figured out, all we'll have to do next is integrate, of course, with respect to u. After we've integrated, then we will rewrite it again, but now going back into terms of x. Fortunately, this is usually rather easy. And that's the whole process of regular substitution or U substitution. Now, if we kind of go backwards from this, inverse substitution, we will begin with the integral of f of x dx. We will let x equal some function of some other variable. Now, we often do this with trig functions, so we'll make this a function of theta. So that's the big difference here. In regular substitution, u is a function of x, but in inverse substitution, x is a function of some other variable. So some variable is in terms of x, or x is in terms of some other variable. Once we have figured out what function that is, then we determine what dx is. Remember, this is going to be some derivative. But now it's going to have d theta attached to the back of it. Then we will rewrite our integral, our original problem, in terms of thetas. Turns out that this is usually rather easy. Once this is done, we'll integrate. Of course, we are integrating with respect to theta. And then we rewrite back into terms of x. Unfortunately, this last little bit can be difficult. Now, one type of inverse substitution that we see most often is trigonometric substitution. Or trig substitution. In this type of substitution, if in the integrand we have something that looks like a squared minus b squared x squared, then the substitution we want to use, remember it's going to be x equal to some function, we'll use x equal to a over b sine theta. If we have a squared plus b squared x squared in our integrand, then the substitution we want to make is for x to be a over b tangent theta. And if we happen to have b squared x squared minus a squared, notice I've commuted the subtraction from the first example. In this case, the substitution we would want to make is x equal to a over b secant theta. That's going to work out nicely. I just want to quickly kind of go over kind of so you can see the connection here. Let's take a look at that middle case. The other two cases are similar, but I'll take a look at if we let x equal to a over b tangent theta, then you'll notice that dx is a over b secant squared theta d theta. Also notice that we can take this and solve for tangent of theta. That would be bx over a. Now, trig functions are based off of right triangles. So if there is our theta, then tangent opposite over adjacent, the opposite is bx, the adjacent is a. That leaves the hypotenuse, using the Pythagorean theorem, is a squared plus bx squared. Notice that that includes a squared plus b squared x squared, which is what is in our integrand. And that's kind of roughly why we end up using those substitutions. But moral of the story, for trig substitution, these are the things to remember. If we have one of these in the integrands, then our substitutions will include x equal to some function of theta. Hope this helps. Enjoy!